In this video, we're going to take a look at section 10.3.1 in one of our, probably our second to last hypothesis test for this semester. So in this section, we're going to be interested in trying to test to see if two variables are independent. Now, we've dealt with this word independent when we worked with probabilities way back several chapters ago. And we said the following: the events A and B are considered independent. They were independent if and only if we had this equation here satisfied. You might have remembered checking something like this equation, and we had kind of always put a little question mark kind of above this equal sign here. We tested things on both sides. Now, calculating probabilities in the real world is sometimes very difficult to do. It's easy with certain probability experiments like rolling a die or picking cards out of a deck or some of the things that we did back in chapters 3 and 4. However, in general, this is very difficult to determine. Like if I wanted to know what's the probability that when I go ask somebody in my town a political question, whether they'll typically stand on the side of a Republican or a Democrat. Like I have no idea what that probability is going to be. What's the probability that like I need to have a tooth fixed or something like that by my dentist within the next couple of months? I don't know the likelihood. But we might be able to try to go ahead and see that if we could test, could we find enough evidence to believe that two events and their probabilities would satisfy this equation, meaning that the two events would be independent. So to help with that, we're going to have what we refer to as a chi-squared independent test or independence test. And ultimately for this test, we're going to see that our hypotheses, much like how they were in the last section, are not going to be really written with symbols, but rather with words. What we're going to have as our H0 hypothesis always is that the two variables, whatever it is that we're comparing, the variables of blah and blah, are independent. So our null hypothesis is always the variables are independent. And the H1 is going to be that they are dependent. Remember is that in hypothesis testing, we're always going to be starting by assuming that the null hypothesis is true. So we're going to start by assuming that these events are independent and then try that hypothesis on and see how it fits. The reason that we do this is that it's a lot easier to go ahead and compute probabilities if we're working under the assumption that they are independent than if they are not. So ultimately, what we'll see at the end of the day is that if two variables are independent, then what that will really mean is that knowing that a member of a population has characteristic A, maybe they meet the description from the first variable, if they're independent, then that means that knowing something about the first characteristic gives us no information about if the member of the population also has characteristic B. In the similar way, if two variables are dependent, then knowing that something meets characteristic A, it has the first variable attributed to it, does not give us, does give us information as to if they have characteristic B. So ultimately in this section, as I state here, we're going to be interested in seeing if the results of our sample are what we would expect to see if the variables being tested are independent. And we will use the test statistic of chi-squared to compute how close the observed frequencies are to expected frequencies, just like in the last section. Okay, so we're going to go ahead here and take a look at a first example to try to at least get some context and see if we can understand a little bit about maybe how this would work. All right, so take a look here at example number 1. A random sample of 500 children, 250 boys and 250 girls, were asked to identify their favorite color. Okay, so suppose we obtain the following data. So you can see here I've organized this in a nice table, and I can kind of see here that each of these numbers represent either a total number of people in a category or some overlap. So here, like this first number of 107 tells me that there were 107 boys who said blue was their favorite color. Okay, and in total I have 500 individuals that were surveyed. So ultimately, I could ask the question, what are the hypotheses that we could use to test to see if a child's favorite color is gender dependent? That is it maybe more likely that boys select certain colors as their favorites? Is it more likely that girls select certain colors as their favorites? I don't know. I might have a hunch, but I want to see if the evidence would actually lead me to believe one over the other. So maybe a good H0 that I could have here is that a child's gender and favorite color are independent. They have nothing to do with each other, right? There's no relationship between them. I might even put that over here on the side. I'm claiming that they are not related. Well, if I compare this to an alternative hypothesis that would say a child's gender and favorite color are dependent, what I'm really saying here is that these variables are related. So this is what I'm maybe trying to decide. Are these two variables related or are they not? And, maybe you could imagine a reason why someone might want to know this. Maybe like, as I think we'll see in a later example, maybe like a toy manufacturer wants to know something about like, well, hey, if I print this particular thing or if I create this particular toy with a particular color, is that going to make it more or less marketable? Maybe I want to know something like this. Well, if I wanted to start to think about how I could begin to figure out which of these hypotheses I might side with, I again have to remind myself, which hypothesis do we believe is true right from the beginning? And again, we always believe age 0 is true until we have enough evidence to change our mind. Right? This is our standard innocent until proven guilty sort of position that we take. Okay, so let's begin by assuming that a child's gender and favorite color are completely independent. They're not related in any way. Well, how would I begin to answer a question maybe like part C? How many of the individuals in the survey would we have expected to be boys and say that blue is their favorite color? So what we can see is in this chart, we know what we observed to be true, right? This is all values that were observed, but now we want to ask, if H1 was true, what would I have expected to see? All right, so in order to compute that, I would say, well, let's see. If I was going to go ahead and state that the variables are independent, I could say, if we believe that the variables are independent, then it should be the case that if I wanted to know what's the probability that I get a boy and someone who says that blue is their favorite color, if the variables are independent, then that should just be equivalent to the probability of selecting a boy times the probability of getting someone who likes blue. That is, I'm just using that identity or that formula that we had when we said that two variables were independent. So, well, let's see. I should be able to figure this out. I know that total there were 250 boys out of the 500 individuals, and I know that there were apparently 200 individuals that said that they liked blue out of the total 500 individuals. And I think if I multiply this out, you can double check me, but I think this comes out to be 20%. So, if these variables were independent, I would have expected 20% of all the people in this survey to have been boys that said blue is their favorite color. So, out of the 500 kids surveyed, we would expect, let's see, I would do 20% of 500. I think 20% of 500 is going to be 100 boys who like blue. This is what we would have expected to see. So if I was to go ahead, I could kind of down here in part D start to put together a table of not the things that I observed, but all the things that I would expect to observe. And we've already kind of seen that I would expect to observe 100 boys that like blue. Now, when I look back at the previous table, I see that I didn't get 100, but I got something pretty close. I got 107. So we might wonder, why was there a difference? If I thought I should have seen 100, why did I get 107? And again, our two explanations are, well, that's just kind of happened just by luck. It's no big deal. You just got a little lucky, random chance. Or we could say, well, no, that shows us that this idea of the variables being independent is just no longer a good fit. So we need to try to figure out, though, what we would have expected to see across all of these different categories. So I'm going to go ahead and try to repeat this here for, let's say, all the rest of the different boys and the colors that they like. Now I'll quickly go ahead over here, kind of up in this space, just do my quick computations, and I'll erase them pretty quickly after. But take a look. If I wanted to do boys that liked green, I would have to do the probability of, I would write out pretty much exactly the same line, but I would just replace blue with green. Notice that when I get to my calculation then, I would still have 250 boys out of 500, but now I'd have to say, out of the 500 original people, how many were people that liked green? Well, there were 150. So, if I was to go ahead and multiply this stuff together, I could see what percentage I ultimately end up with. If I swapped over to my calculator, that would be, let's see, 250 boys times 150, and then we just, oops, I forgot to do my divide by 500. Let me back up and do that so it looks just like what we wrote down. So I have this, and then times 150 divided by 500. That comes out to be 15%. So then I could say 15%, oops, of all of the people should be boys who like green. So what's 15% of 500? Well, if I switch over, 500 times 15%, that should be 75. Now I could continue doing this for each of the individual boxes here, but I'll go ahead and speed up the process, and you can try to see if you could figure out or confirm that the values I'm writing down here are indeed correct. But I think I would also end up with 50 boys who say that pink is their favorite color, and 25 that say yellow. The interesting part here is that you'll notice that all of my calculations when I switch to girls that like different colors is going to be pretty much identical, because instead of having 250 over 500 for boys, I would swap out girls and I would still have 250 over 500. So the starting fraction won't change when I go to girls. The second fraction will, but they'll just change as I move along the colors. And so I'm going to end up with the exact same values down here. So this would be a table for the number of children we would have, again, expected to see in every category. So let's go ahead and try to take a look here at, again, what we observed versus what we expected, and kind of see how close we are. All right, so what we thought we were supposed to get 100 in each of these, 75 for each of the greens, 50-50 split over here, and a 25-25 split. Wow, so this part is exactly what we would have expected to see. So this makes us feel really good about H0. The other colors categories maybe make us feel more or less certain about H0. And so what we want to do is to have a test that will help us measure the weight of the evidence, what we've observed, compared to what we expected to see. If what we expect to see is pretty close to what we observed, then we'll stick with H0. And if it's pretty far away, we'll get rid of H0 and go with H1 instead. This kind of gives us a nice outline of the test that we're going to be running in this particular section. And I'm going to go ahead and summarize it quickly here on the next page. We'll see again that we still have the same standard four-step process. We have our hypotheses. The variables are independent, is always our H0. Our test statistic, we're going to have to go ahead and start by inputting all of our information into a matrix in the calculator. If you haven't used matrices before, don't worry about it. It's not too terribly difficult. We'll have some conditions to check. we'll have actually the same exact test statistic we did last time, but everybody should have this test on their calculator. We'll then go ahead and actually run a chi-squared test, not a GOF, but just a regular old chi-squared test on the calculator. We'll still draw our picture, compute a p-value, and it'll always be a right-tailed test. And then we'll be able to state a conclusion. Okay. We'll see that this test is actually surprisingly easy to run, and we'll take a look at how we could generalize everything that we did in the first example in the next video.